In this problem, we're asked to find the electric field between the regions made up due to two parallel non-conducting sheets. So if we assume that we have the positive charge, then we know that the electric field due to the positive charge distribution is going to be away from that charge distribution. So to the left of the positive sheet, it will be going to the left. To the right of it, again, it will be going to the right. And then it doesn't matter whether we have this negative charge distribution or not. On this side, the electric field due to the positive charge distribution will be going to the right. On the other hand, for a negative charge distribution, then the E field is going to be heading towards the negative charge. So we know that E minus is going to be heading towards the negative charge distribution, and E minus will be heading towards the negative charge distribution in both of these cases. And now, because these sheets are non-conducting, we know that they are fixed in place, the charges. And we also know that the electric field for these sheets is given by the charge density over 2 times epsilon naught. So if we want to find the electric field for the positive charge distribution, that's going to be sigma plus over 2 epsilon naught. And sigma plus is given as 6.8 times 10 to the minus 6 coulomb per meter squared, all over 2 times sigma epsilon naught, which is 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. We do this and we get about 3.84 times 10 to the 5th Newton per coulomb. Similarly, E negative would be sigma negative over 2 epsilon naught. Sigma negative is given as 4.3 times 10 to the negative 6 coulomb per meter squared over 2 epsilon naught. And if we do that, we get a value of about 2.43 times 10 to the 5th Newton per coulomb. And now, if we look at to the left of the plus distribution, we're going to find out that, let's call it the electric field on the left, is going to be the difference between E plus and E negative, because they're going in opposite directions. So it's a difference between them. Since we took E plus first, if we get a positive answer, then we know that the direction of the left side electric field is going to be in the direction of E plus. If we get a negative answer, it will be in the E minus. And if we plug these numbers in, we have 3.84 times 10 to the 5th Newton per coulomb minus 2.43 times 10 to the 5th Newton per coulomb, which gives us a value of 1.41 10 to the 5th Newton per coulomb this, since this is positive, it will be in the direction of E plus, which is to the left. In between, if we look at the electric field from our picture, we notice they're pointing in the same direction, so we're going to add those two up. This will be E plus plus E minus, and since they're both in the same direction, we already know it's going to be to the right, because both of them point that way. And again, 3.84 10 to the 5th Newton per Coulomb plus 2.43 times 10 to the 5th Newton per Coulomb, which is the same as 6.27 times 10 to the 5th Newton per Coulomb. Again, we already said it's to the right, and then to the right of E minus would be our last region to look at. If you look at this graph, you know that they're going in opposite directions. So again, if we take E to the right to equal E positive minus E negative, whatever direction we get will depend on whether it's positive or negative. So this is 3.84 times 10 to the 5th Newton per Coulomb minus 2.43 times 10 to the 5th Newton per Coulomb. We already know this is 1.41 times 10 to the 5th Newton per Coulomb. But now, because it's positive and we picked E plus first, we know this is going to the right. So we know this is to the right. So when you're doing these type of problems, you can always pick the bigger value minus the smaller value, but keep in mind that the direction is always going to be in the direction of the bigger value. That we notice, because E plus was the bigger, in this case it was to the left in part 1, and then in the last part it was to the right, so it's not always the same.